We are now going to see the three unknowns for part A. So you'll want to label these in the boxes A, B, C from left to right. These unknowns are all taken from the video that you just saw. So you have just seen videos of the three unknowns. If you need to, go back and watch them again. I know that they do go by fairly quickly, but at this point I'm going to continue on to the next topic. And that will be electron configurations. Now, you should have already discussed this in some depth in your lecture, but I'm just going to take a moment here and review this topic briefly. So if we are to really look at what electron configurations are, they're kind of like addresses for the electrons in an atom, telling us where they live. It's essentially a list of the subshells, and those are put in order from the lowest energy to the highest energy, and information as to how many electrons are in each subshell. For the atoms, the order that these subshells are filled is going to be consistently the same. And by just looking at a periodic table, we can figure out that order. This is not 100% true for all of the atoms, but for the ones that you are going to be concerned with, they will follow a preset pattern. So we will always fill 1s subshell first, then we fill the 2s subshell, then the 2p subshell, etc. And then what we do is after each subshell, we list as a superscript, that is a number kind of like an exponent, that tells us how many electrons are in that particular subshell. So if you go ahead and look at this electron configuration, if we are to read that from left to right, it tells me the 1s subshell has 2 electrons in it. Then the 2s subshell has 2 electrons in it. Again, that's that superscript there that tells you how many electrons. 2p has 6 electrons, and 3s has 1 electron. Notice that there are no spaces, there are no commas, and that these number of electrons are always written above the as a superscript and not down lower. If you compare this picture to the periodic table, you'll see that it's essentially the same general structure. You might notice that where helium would be is missing. But other than that, this follows the general pattern that we would expect for the periodic table. And this is going to tell us the order that the subshells fill. So if we look at the periodic table, period 1, we first fill 1s. All of the elements in this 2-column group over here are called the s block. And I've just moved helium over for the purposes of doing this. And after filling 1s, we go to the next row, we fill 2s. And then after 2s, we fill 2p. And after that, you go on to the next row, 3s, 3p, 4s, 3d, 4p, etc. Now, some things that you'll want to note here that might be a little bit confusing, and that is that we don't fill the 3s completely before we start 4. We fill 3s, then 3p, and then 4s before we fill 3d. And then continuing on here, it's just like if I'm reading the atomic numbers, so I'm just going in order left to right. After 3d, 4p. After 4p, 5s. Then 4d, again, you'll notice that we kind of went back by a shell number, 5p. So a thing to note real quickly, that is that the s block, the subshell number matches the period number. So these are 1s in period 1, 2s, period 2, 2p, period 2, 3p, 3s, period 3. The D block elements are always going to be, the subshell number will always be one behind the period number. So in row 4, period 4, these are the 3Ds. Period 5, 4Ds. Now if you compare this to a periodic table, you'll see that after 6s, we have the element lanthanum, which is usually shown in the 5Ds, and then we skip down to the 4Fs. So the order is generally going to be 6S, 4F, then we go back to 5D, 6P, then 7S, we do the same thing, we skip down to 5F, 6D, 7P. Orbitals describe a region in space in which you are most likely to find an electron. In other words, it's showing the probability of electron being in a particular area of space. A very important rule to know is that an orbital can hold at most 2 electrons. So that means the only possibilities we have is an orbital has 1 electron, 2 electrons, in which case we say it's full, or it's empty. That's it, no other options. You'll want to focus a lot on the terminology from here on out. So every shell, that is energy level, has an S subshell. And remember, we listed subshells as 1s, 2s, 3s, etc. And every S subshell has only 1 orbital. So that means that an S subshell with 1 orbital can never hold more than 2 electrons. So 1s can have 1 after it, or it can have 2 after it, nothing else. 2s can be 1 or 2, no higher than 2 on any of the S subshells, because they have 1 orbital, and an orbital can only have 2 electrons. Moving on to the P's. Except for the first shell, every shell has a P subshell. So there's no 1P, but there is 2P, 3P, etc. Let me say that again. 3, 2, 1. So there is 2P, 3P, etc. P subshells contain 3 orbitals, unlike S, which only contained 1. And remember what we underlined up here? We said that an orbital can hold 2 electrons at most. So 3 orbitals, 3 times 2, would mean we can hold up to 6 electrons. So here's a reminder again. Orbitals can hold at most 2 electrons. Starting with shell 3, we get D subshells, 3D, 4D, etc. D subshells always come in sets of 5 orbitals, and 5 times 2, this means it can hold up to 10 electrons. And then finally, starting with shell 4, we get an F subshell. So there's 4F, 5F. And an F subshell contains 7 orbitals. So 7 times 2 would be 14 electrons. You'll notice the pattern. S subshells have 1 orbital, P have 3, D have 5, F have 7. It's the odd numbers. And remember, maximum number of electrons is just that number times 2. So let's do some practice here. So use a periodic table to find the electron configurations of fluorine, scandium, iodine, and bismuth. I'm going to go ahead here and put up a periodic table in just a moment so that you can practice with that. And what I'd like you to do is pause the video and attempt to find the electron configurations of these 4 elements. So here is a periodic table. Go ahead, pause the video with this on the screen, or just use a periodic table that you have available to you. Okay, so we're going to go ahead and start with fluorine, which is right here on the periodic table. And what we do is we fill in order the 1s's, right? So 1s has 2 electrons, just like it has 2 elements, 2 electrons. Then we fill the 2s's, so 2s, 2. Then here we're at the 2p's, so 2p, 1, 2, 3, 4, 5. 2p, 5. Make sure that you're writing it down exactly as you see here, with the numbers superscripted for the electrons. The next element we will look at is scandium. So you'll notice we always begin 1s2, 2s2, 2p6. Now we move on to 3s2. Back to the p block here. So 3p6. Then move on to the 4s's. So there's 2 boxes, so 4s2. And then remember, this is not 4d, this is 3d. The d's are always one behind. So this is 3d1. Titanium would have been 3d2, vanadium would have been 3d3, etc. Now we move to iodine, which is a little bit lower in the periodic table, and I'm going to want you at this point to start using the shorthand notation. So the shorthand notation means that we go back to the last noble gas that we saw, and we just start counting from there. So the noble gases, remember, are in group 8A. So for iodine, go backwards, do not pass go. Backwards would be krypton. Okay, so we're going to just write krypton in square brackets and then start writing the electron configuration from there. So you see how I've done that, krypton in square brackets. So after krypton, we go to the 5s's. So this is 5s2. These are not the 5d's, remember these are the 4d's. So 4d10. And then we're back in row 5 again, so 5p's. These are the 5p's. So 5p, 1, 2, 3, 4, 5. 5p5. And finally, let's look at the most challenging one, which is bismuth. And with bismuth, we're going to do the same abbreviated notation. We don't want to write out everything, or it will take up essentially a whole column of paper. So we're going to go back to the last noble gas that it passed. So the last noble gas before bismuth was xenon. So I'll write xenon in square brackets. And then these are going to be the 6s2s. Now let me click here and move on to the full electron configuration. So we've done the 6s2s. On this periodic table, this is presented in kind of an odd way. Lanthanum is usually written up there, and actinium is usually written up there. So we fill 6s2, and then rather than saying 5d1, then going to the 4f's, it's just more convenient to say 6s2, 4f, 14. Remember, these are technically in the 6th period. That's where they would fall. So the F's are 2 behind. So 4F, 14. And then the D's are up to 10. So these are the 5D, 5D10. And then 6P, 1, 2, 3. I would never ask you for an electron configuration for any of the elements in here. number one, most of them are going to be exceptions to the rule that in terms of how we count them, and so our usual way of predicting electron configurations would not work. So I'm very much being selective about which elements I pick. I'm picking only ones that I know the procedure that we've learned will work correctly. Another important term is valence electrons, as well as the term valence shell. So the valence electrons are the electrons in the outermost shell or energy level of an atom, and we call that outermost shell the valence shell. The valence shell differs from element to element. So let's take a look at aluminum's electron configuration. So 1s2, 2s2, 2p6, 3s2, 3p1. You'll want to have a periodic table in front of you while we're doing this. So which shells have electrons? Not subshells, not orbitals, shells. So remember, these numbers are the shell numbers. 1s is a subshell, but it's on the first shell. 2s is a subshell on the second shell. So we look at the larger numbers here. So 1, shell 1 has electrons. 2s2p, so that's shell 2 has electrons. And shell 3 has electrons. So shells 1, 2, and 3. Again, also called energy levels. Now, look at the one of these which has the highest number. So the highest number in this list is 3. We're going to call that the valence shell. So when you look at an electron configuration, it's always the shell number with the highest number. So 3, 3, 3 is the valence shell. That means the electrons that are spending their time furthest away from the nucleus is going to be the third shell for aluminum. How many valence electrons does aluminum have? And where are they? Well, we've already decided that the valence shell is the third shell. So we look at all the subshells that begin with 3. And those would be 3s and 3p. 3d doesn't have any electrons in it at this point, so we only look at 3s and 3p. 3s has 2 electrons, 3p has 1 electron, so those are the valence electrons. 2 plus 1, 3 valence electrons. Now, instead of going through this whole process of adding up the number of valence electrons based on the electron configuration, it turns out there's a much easier way to figure out the number of valence electrons. And it's a very important piece of information, as we are going to see when we talk about bonding. So it's critical that we know the number of valence electrons. So for all of the elements in the groups ending in A on the periodic table, the number of valence electrons is simply the group number. That's it. So helium is an exception to this. Helium, as element number 2 on the periodic table, only has 2 electrons. Even though it's in group 8A, there's no way it could have 8 valence electrons. So helium has 2. Let's take a look at the periodic table here to see what I mean by the group numbers. You'll notice there's a new way of doing it, 1, 2, 3, 4, just numbering them to 18. And that method isn't generally very useful, so I'm not going to ever refer to group numbers using these numbers. Instead, I'm always going to use these numbers here that are headed with Roman numerals. So this is 1A, 2A. I'm going to skip these for a moment. 3A, 4A, 5A, all the way to 8A. Some people call this group 0, but I prefer 8A. These numbers are not the ones that end in B are not going to be very useful to us, so I'm not going to generally refer to these, and you'll see why in a moment. They are not practical. Now let's take a look at the valence electrons for transition metals. The transition metals all have group numbers that end with B when we look them up on the periodic table. And it turns out that, with a few exceptions that we don't need to worry about, those elements have 2 valence electrons. Let's see if we can figure out why. So we'll start by looking at the electron configurations of the first three transition metals. So here we have scandium, here we have titanium, and here is vanadium. You'll notice the electron configurations only differ in the 3D subshell. So 3D has 1 electron for scandium, titanium has 2, vanadium has 3. Which of these shells have electrons? Well, the first shell, the second shell, 2s, 2p, the third shell, 3s, 3p, and 3d, and the fourth shell. Which of those is the valence shell? Remember, it's the highest number. So the valence shell for all of these atoms would be 4. So we don't care at all about the 3Ds. We only care about the 4s electrons. And since all of those elements have 2 electrons in shell 4, they all have 2 valence electrons. And as we keep adding d electrons, that has no effect. It doesn't change the fact that these elements all have only 2 valence electrons. So it's not until after we fill the 3D subshell that we start adding additional valence electrons. I'm now going to give you a set of questions of mixed difficulty that are similar to the questions that you're going to see on the lab report. So by answering these questions, you should be fairly well prepared to answer the questions on the lab report. So take a moment here and try to answer as many of these as you can. If a term is unfamiliar, please look it up. And from there, you should be able to answer the questions that you're going to need to answer on the lab report. So pause the video, and in a moment I will go over the answers to all of these. All right, so let's take a look at these questions. Which subshell is being filled by the element with atomic number 27? So subshells, remember those are 1s, 3d, 4f, those kinds of things. Okay? So let's look up atomic number 27 on the periodic table. 27 is cobalt. To figure out which subshell is being filled up, we just look and see where it is on the periodic table. It's in the 3Ds. So the 3Ds are the subshell being filled with cobalt. What is the maximum number of orbitals and electrons in a 4D subshell? Well, this answer would pertain to all D subshells. We know that D subshells always come in a set of 5 orbitals. So the answer to A would be there's 5 orbitals. And if we fill those completely with electrons, each orbital can hold 2 electrons, so 5 times 2, 10 electrons would be the maximum number that could fill a 4D subshell. What is the first element that fills the 2s subshell? So fills means it has to have all the electrons it can hold. S subshells can hold 2 electrons. So it's the first element that has 2s2 in it. What would that be? Well, these are 1s's, so that fills the 1s's. Here are the 2s's. So this would be 2s1 with the 1s2 in front. And beryllium would be 1s2, 2s2. So beryllium is the first element to fill the 2s's. Just like we would say neon is the first element to fill the 2p's, and magnesium the first element to fill the 3s's, etc. We just say it's the last element in the group fills it. Which element has a half-filled 3D subshell? Half-filled. Well, filled would be how many electrons? Well, we already answered a moment ago that 10 electrons would be in a D subshell. So half-filled would be 5 electrons. So 3D with 5 electrons, 3D5. So 3d5 would be 1, 2, 3, 4, 5. It would be manganese. Manganese. What is the alkaline earth metal in period 4? The alkaline earths are group 2A. So we need to find the element in period 4, group 2A. So here's group 2A, and here's period 4, so that element would be calcium. What is the first element with 6 3d electrons? Well, let's see if we can find that. So we'll go to the 3d electrons. So where do we fill 3d? Well, these are the 3ds. So we would expect 3d1, 3d2, 3d3, 3d5, 3d6 would be iron. Iron. What is the element in period 5 with the same group as neon? So the element in period 5 in the same group as neon. So where is neon? It's in group 8. So that means we want the element in group 8A in period 5. Period 5 is right here. This would be xenon. And finally, what is the first element that completes n equals 4? Okay, that's a bit tough. So we know n equals 1, we need 1s. To fill n equals 2, we need what? 2s and 2p. For n equals 3, you have to fill 3s, 3p, 3d. And then for n equals 4, you have to fill 4s, 4p, 4d, and 4f. Let's see if we can find that. So we've filled the 4s's, we filled the 4p's, the 4d's are down here. So cadmium fills the 4d's. To fill the 4f's are right here. So it would have to be this last element right here, lutetium, Lu, would fill the 4f's and thereby fill all of the fourth shell. So to complete part B, what you're going to want to do is fill in the table on the top of page 56. I'm going to give some special instructions for this. So I'll want you to write out the full electron configurations for those first 6 elements. So everything, 1s2, 2s2, etc., up to bromine. Write them all out nice and neat. For the rest of the elements, starting with strontium on that assignment, use the shortcut notation instead. In other words, you're going to start with a noble gas, write that in square brackets, and then start counting from there, just like I did in the video for iodine and for bismuth. Wherever you're asked for a group number, always answer with the group number with A's or B's. Don't use the group numbers that are 1 to 18, etc. So for example, group 13, call it group 3A instead. And I would rather that you use Arabic numerals, so 3A, instead of Roman numerals like you see written there. Be very careful in answering question 2 and question 3. As I say there, those can be tricky, and that's kind of why we practiced a moment ago with that looking deeper section. A note, your lab manual uses the word sublevel instead of subshell. I've never seen that term sublevel used before. Subshell is the standard term, so if you want to change that from sublevel to subshell, please do so. And if you get stuck on any of those questions in Q2 and Q3, you'll want to go back and look at the looking deeper questions I asked just a moment ago, because you should find that there's a similar question in all of those relative to the questions you see in Q2 and Q3. So if you can see how I answered a question on my video, you should be able to answer a similar question on Q2 and Q3. So you'll probably want to pause at this point and finish that, but I'm going to continue the video with part C on atomic radius, which is fairly short, and I just want to cover that and keep this all in one video. Part C is largely about constructing a graph and interpreting information from that graph. So what you'll be doing in part C is building a graph of the atomic radius data that you see listed on page 51. Now, in constructing this graph, we need to know the extreme values. That is, what is the lowest atomic radius and what's the largest atomic radius. We need that information to figure out how we're going to scale our graph. So hydrogen has the smallest atomic radius, and that's 37 picometers. And then of the elements that are listed on page 51, you'll see that potassium has the largest radius at 231 picometers. So we want to be able to capture all of that information on a graph, and we also want the graph to be easy to read without any of the points being compressed. So the way you're going to want to do this is, as you're counting up what would be the y-axis, the vertical axis, you want each box to stand for 10 picometers. So the very bottom line would be 0 picometers. The next line above that would be 10. The line above that would be 20, 30, etc. And you don't want to label every one of those lines because that would make the graph look very messy. So label every 50 picometers. So you should have a line for 50, you should have a line for 100, a line for 150. And then, so on the very bottom square, as I'd said, you're going to start with 0 off to the left, to the very bottom line on the graph. Go up 5 squares, and then that line is 50, 100, etc. And if you've done this correctly, you don't have enough to go to 250, but you should have enough to go to 240, so you'll want to go ahead and mark that last line as 240. When you're marking your data points on the graph, you want them to be dark, but not very big. So very dark, but small dots. And then connect the data points using your ruler with a fairly dark line. I should still be able to see the data points themselves. So the circles need to be large enough that I can see them over the line. So keep the line very thin but dark. Finally, answer questions 4 and 5 in complete sentences, and be sure that you have appropriate scientific terms in your answers. So don't just answer, it goes down, it goes up, it increases, it seems to go down, something like that. Those are not acceptable answers, and you will not receive credit for answers like that. So before you answer those questions, please reread page 49, because that will help you out. And on question 5, this is being specific in terms of the terminology you want to use. You might want to use the words electron configurations and shells, and you might want to compare atoms in period 2 to those in period 3. Specifically, what is different about the elements? What would be different, for example, between lithium on period 2 versus sodium on period 3, right below it? And that's going to have an important effect on being able to answer these questions. That is the end of the videos for experiment 5. Thank you, and good luck with this.